going to take a quick look at the homework that we had last night. It was your forces worksheet questions number 1 to 10. Have a look at the answers up on the board here right now. And then you can let me know in a second, once you've had a chance to compare them, which ones we need gone over and which ones we don't. All right, which of these questions do we need gone over? Kathleen? 2? Yep. Yep. 10? Oops, I got 4.91 for both 9 and 10. I'm not sure if that's right. Let me just check my answer sheet myself, and I might have just typed that wrong here. Give me 2 seconds. Those are both right, actually. It should be 4.91 for both of them. Any others besides 2 and 10? 4, 2, 4, and 10. Going once. 2, 4, 5, 9, 10. All right, let's do 5 of these questions here, okay? Number 2 says, calculate the force of the floor pushing up on the person in the elevator. When we're looking for the force of the floor, that's really the normal force acting on the person, right? What pushes on the person? The normal force, whether that be the floor or whether that be the chair that the person's sitting in, whether that be the roller coaster seat or the roller coaster track, okay, whatever it is it's pushing up on the person, that's the normal force. So that's really what we're solving for here, is the normal force. We draw a free body diagram where we have a force of gravity acting down on this person and a normal force acting up on this person. Can anybody tell me why I drew the normal force shorter than the force of gravity? How did I know that it should be shorter? Yep. If it's moving downward, the downward force must be bigger, right? Larger. Yeah. If it's moving upwards, accelerating upwards, then the upward force must be bigger. Okay, I drew the force of gravity bigger because it's accelerating downward. All right. Okay, next step is the same as it always is with this question or any other. The net force is equal to the sum of the forces. The net force, the total force, all of the forces added together, Fn plus Fg. In this case, Fn plus Fg. Now, that next step is m times a, the mass times the acceleration. Really, that's just 2 relationships, right? The net force is the total force, and the net force is ma. So now if the net force is equal to both of those, then both of those should be equal to each other. Ma is equal to Fn plus Fg. The mass here is 50 kilograms. We're given that value. We're also given the acceleration. We're going to make it negative 2.00 meters per second squared. Why the negative? Why the negative? I didn't give it to you in the question as a negative 2. I said it was 2 down. Why negative, Joe? Yeah. It's downward. And whenever we have something that's downward, we're going to make it a negative value. Fn is what we're looking for. Fg is 50 times 9.81. Correct? Not quite. 50 times what? Negative 9.81, because the force of gravity is acting down. Just like acceleration was downward, we made a negative. Gravity is negative, so we make it downward as well. Okay, 50 times 2 is 100. We get negative 100 on the left-hand side. 50 times 9.81 is subtract 490.5 newtons. We take the 490.5 over by adding, and when we do, we should get 390.5, I think, right? Which was 3.91 times 10 to the 2 newtons, or 391 newtons. All right. Anybody that had trouble with that? Do you want to volunteer what the trouble was? What was the issue? No, all right. Next question we did was number 4. The weight of the person in the elevator. This is a simple question. Sometimes we overlook this simple. Right? We say, well, it can't be that easy. The weight, the apparent weight in question number 3 is the normal force. Whenever you're looking for how heavy you feel, it's the normal force. They talk about people and the astronauts in the International Space Station as being weightless. They have no weight. Is that true? They absolutely have weight, almost as much weight as they do on Earth. Weight is the force of gravity. What they don't have is an apparent weight. They perceive no weight. Because apparent weight, how heavy they feel, what their perceived weight is not how heavy they really are. Rather, it's the normal force. And in space, when you're orbiting the Earth at 400 kilometers above the surface, in the International Space Station, you have no normal force acting on you. You feel weightless as a result of that. But you still have weight. Weight is just the force of gravity. If we want to find the force of gravity, the weight, all we're going to do is multiply m times g. It's 75 times 9.81. And it works out to be 7.36 times 10 to the 2, or 736 newtons. Now, if you did this and made 9.81 a negative value, you would have got a negative weight, right? Doesn't make a whole lot of sense, does it? A negative weight? No. It's okay. Technically, weight is the force of gravity, so we could call it a negative value. Either one I'd take here. Okay, positive or negative value there would work. Right? In question 4, when you see it done, it's certainly a lot easier than question number 2 was. It's just a matter of recognizing what you need to find there, right? All right, the next question we need to go over was number 5, which said calculate the acceleration. We've got a force acting down on the 5 kilogram object, and we have no other forces. It's not quite true. We have a force of gravity here and a normal force here, but these two guys cancel each other out. So the only one that's left is the force of gravity acting on the 5 kilogram object. The net force is still equal to the sum of the forces, but in this case, it's only one force, the force of gravity. Now, the net force is also equal to what? Net force is always also equal to what, Kathleen? Yeah, it's good. It's mass times acceleration. The mass is 7 kilograms. On the left-hand side, when you're attaching it to the acceleration, you're going to use the total mass because the total mass is what's being accelerated. 7 kilograms times the acceleration equals 5 kilograms times 9.81. Some of you may have redrawn this way. Okay? I think it's a good idea, in fact, if you do. If we do, then the force of gravity ends up being to the right. Therefore, I'm probably going to make that 9.81 to the right. Solve for A. 5 times 9.81 divided by 7 gives me a value for question number 5 of 7.01 meters per second squared. Kathleen's question was, we got a positive acceleration here. Does that mean that it's going down, or is the 2 kilogram block pulling it back up? It's going down. Okay, it's going down, but my positive acceleration is based on this diagram, not on this diagram. So in this diagram, the system is moving to the right. Well, it's not really moving to the right. The 2 kilogrammer is, but the 5 kilogrammer is moving down. So basically, if you get a number here consistent with this diagram, that's fine. Because in the end, how do you express it as a positive or negative? Really? How do you express it as a positive or negative? Well, this one's moving to the right, which you'd say would be positive, right? This one's moving down, which you'd say would be negative, so which do you go with, right? Okay. Don't worry about the positive or negative. Just get the magnitude of that acceleration. And then if they ever asked you specifically, what's the acceleration of the 2 kilogram object, you'd say 7.01 to the right. Okay, the 5 kilogram object, 7.01 down, you'd say. Okay. All right, we had question number 9 as well. Number 9, almost the same question as number 5, except we had 3 objects here. Let's redraw it for number 9. We have the 3 kilogram, we have the 2 kilogram, and then we have the 5 kilogram. There's no other forces other than gravity acting on the 5 kilograms, so we'll just call that Fg. The net force is equal to the sum of those forces. F net is equal to Fg, that's it. M times A is equal to Fg. And M, what mass do we use? The 3, the 2, the 5, or the combination of them? What mass is being accelerated here? The 3, the 5, the 2, or the combination of them? 2, the 5, the 3, they're all being accelerated, right? So let's use the total mass of 10 kilograms equals the mass of the 5 kilograms times 9.81. Why do we only use the mass of the 5 kilograms for gravity? Well, the reality is there's a force of gravity pulling down on these guys, but there's also a normal force pushing up on these guys to cancel. The only net force that causes it to move would be the force of gravity acting on the 5 kilogram, not the other ones. So that's the only mass we include on the right-hand side. On the left side, it's the whole mass. On the right side, it's only the mass that's being pulled on by gravity. Yep. Yep. No. I rarely draw those myself in that case. I mean, by rights, we probably should. But in the end, they always disappear. So we can get away with it drawing the normal force and gravity there. I just drew it there more to show you that, yeah, look, there are other forces, but they don't matter to this problem. So what do we get for A there? 5 times 9.81 divided by 10 worked out to be, I think it was 4.91 meters per second squared. And finally, we had question number 10, where we want to find the acceleration of this block here, this 5 kilogram block. These are the ones that, in my opinion, get a little bit harder. It's still the same basic idea, F net is equal to the sum of the forces, but we have to get one of those forces first, and that force that we usually have to get is the force of the hill. So let's draw that. We have gravity acting down. We have a normal force acting perpendicular to the surface. We have the force of the hill acting right here, perpendicular to the normal force and parallel to the hill. Now, I had one or two people in during scheduled help here today asking me questions here about this, and that's great. Okay? That's one of the things this semester that I found about all 3 of my classes actually is that you guys are good at asking questions during scheduled help. I'm busy during scheduled help this year, and that's good that I'm busy during scheduled help. Come and ask me those questions, okay? Somebody, I can't remember who it was asking me this question, said, when we say F net is equal to the sum of the forces, we don't have to put in Fn in Fg. We don't have to put in Fn and Fg. Is that person right? Do we have to put in Fn and Fg? Yeah, we do. We do, right? So why don't I have it put in there? Yeah, we already have them in. We have to include Fn and Mg because they don't cancel each other out like they did in a lot of the other questions. But we have included Fn and Fg. We've just done it in a simpler way. Okay, we've combined them to get Fh. Fh is not a force. Okay, it's a non-existent force. It's the combination of 2 other forces already, the forces that we have to include. So F net is equal to Fn and Mg, but we're going to simplify it by saying F net is equal to Fh. F net is m times a. Fh is, we got to find that, don't we? What angle is that right there? 30 degrees. Let's say sine 30 degrees is equal to opposite over hypotenuse. That's going to be Fh over the hypotenuse, which is m times g. 5 times 9.81 times sine 30. Works out to be, I don't have that answer on my sheet. I think it's 24 point something. 525. Thank you. The mass is 5. So now when we divide 24.525 divided by 5, we get 4.91 meters per second squared. All right? Okay? I think we're pretty much ready for a quiz, eh? We won't have it today, but we'll have a quiz tomorrow on this multi-force, the multi-force stuff. What have we got with multi-force stuff? We've got the elevator, we've got the pulley type problems, we've got the hills, the inclined planes like this. Okay, you'll probably see a couple of those things on tomorrow's quiz. Okay, just to get you just a little bit closer to being ready for that quiz, let's spend a few minutes right now before our break here working on questions 11 to 14. Number 14 is a really good one. Why is 14 a good one? It's a whole hill and a pulley, right? Okay, if I give you a question on a quiz and I was telling you that you're going to see, some kind of, maybe a question on hills, maybe a question on pulleys, maybe a question on whatever. Well, wouldn't it be a good idea to give you one that's a combination of it? Okay, spend a few minutes working on these, and then once you've had a chance to do that, we'll take a look at question number 14 to make sure you can do that, okay? All right, everybody, let's take a look at number 14 up here now. Let's draw the picture a little bit simpler here, first of all, okay? We've got a number of forces acting here, okay? We've got a force of gravity acting down on the 5 kilogram. We've got a normal force acting at 90 degrees to the 5 kilograms. We've got a force of the hill that's acting this way, FH. Okay, we'll transfer that FH over here because it's the same value. And we've also got a force of gravity acting down on this 5 kilograms, like here. Now, which forces do we care about? Well, we care about the force of gravity acting on the 5 kilogram, okay, the one that's hanging over. We also care about the normal force and the force of gravity acting on the other one, the two black forces that I have labeled there. But those two black forces, the normal force and the force of gravity acting on the one on the hill, those two forces combine to give me the force of the hill. So in effect, all I care about is the green one and the red one. Okay, I care about all of them, but the red one already accounts for the two black ones. So we won't pay any attention to those black ones any more than we already have. Let's straighten this out a little bit, okay, just to make it look a little bit simpler here. We've got the 5 kilogram object on the left. We've got the 5 kilogram object now on the right. We've taken this one and stretched it out. We've taken this one and stretched it out. That means we have FH acting to the left. And it means we have FG that's acting to the right. Okay, which one's a bigger force? Well, we don't know yet, as we haven't calculated either one of those. So if you don't have the magnitudes of them drawn properly, you don't have the right one drawn longer, okay, than the other one, it doesn't really matter at this point until you know what those forces are. Okay, let's say F net is equal to the sum of the forces. That's FH plus FG. Let's say M times A is equal to the sum of those forces, FH plus FG. And if you're not getting this step, guys, listen, you gotta. Okay, we always do this. Okay, we've done this for the last 2 weeks. F net is equal to the sum of the forces. It's always what we do whenever we have more than one force acting. Trick is recognizing which forces act here. The mass that we're going to use here is 10, because we always use on the left-hand side the total mass. It's M times A. What M is accelerating? The 10 kilograms, the whole thing. Looking for A. FH, we don't know. So let's get that. Let's get FH over here on the left-hand side. Let's say sine 30 degrees, because we know this angle up here is 30 degrees. Sine 30 is equal to opposite over the hypotenuse, which is M times G. FH becomes equal to mg sine 30, or 5 times 9.81 times sine 30. I think that works out to be 24 point something. Somebody have that? 525? Now we plug them in here. FH is negative 24.525 because we have it drawn to the left in my new diagram. FG is 5 kilograms times 9.81, which is 49.05. So neg 24 plus positive 49, you divide it by 10, gives me 2.45 meters per second squared. How many people got that one? Good, good. I'm going to give you the answers to the other two questions as well. So the other three questions, 11, 12, and 13. But I don't want to go over those other three questions at this moment, okay? If you struggled with any of them, then copy this down. Use it as a guide. I'm telling you, if you can answer this question, if you understand this one, then you can do the other ones. So use this as your recipe as you go through the other questions, okay? And then if you still struggle with one of the other questions, come and see me and I'll help you out with it at that point, okay? Yep. Yep. Sorry, why would you use the whole weight or why wouldn't you? So why wouldn't I use the 10 kilograms? Okay, Okay, good question. Guys, can anybody explain here why, when I'm calculating FH here, I don't use 10 kilograms? Rather, I only use the 5 kilograms. Yep, Abby? Yeah, that force is. Okay, Liam, I need to take into account, let's call them object number 1 and object number 2. I need to take into account object number 2. I absolutely do. So you're right as far as that goes. I can't ignore one of the objects, but I am taking it into account. I'm looking at the force of gravity acting on number 2 separately from the force of gravity acting on number 1. Why am I doing it separately? Because the conditions are different. This guy's on a slope, this guy's not. It doesn't mean I can ignore one of them. I can't. But I have to treat them differently because gravity has a different effect on them. Does that make sense? Gravity's acting on this one, and it's pulling straight down on this one. Gravity's acting on this one, it's pulling straight down, but we've got this normal force acting at this funny angle there. Does that make sense? So you have to count. You're right in the sense that we have to do both of them, but we can't combine them unless we had something like that. Liam, could we then combine them? Yeah, we could. In that case, we could pretend it was one object, right? 5 kilogram, a 5 kilogram, be the same thing as saying a 10 kilogram, right? But only if they're both on that slope. Okay. Yep. All right, let's take a look at a problem that's a little bit differently here, guys. This one's not in your worksheet. This is just an example that I want to give you. Unfortunately, it's not in your book either, so you're going to have to copy down the question itself. It says, a 20 kilogram wagon is being pulled to the right with a force of 100 newtons, but that force acts at an angle of 30 degrees above the horizontal. You guys know, when you pull a wagon, right? Anybody of you guys ever deliver like the Flyers or the Western Wheel? I see the person that delivers flyers on my street. They bring a wagon, and there's a couple of them. They have the wagon, and then they have all the flyers in the back, and then they toss them up on the step or whatever. Okay, when you pull a wagon, more like this, right? There's the handle of the wagon. You pull it with a certain force. Maybe it's 100 newtons, maybe it's another force, at an angle of, let's say, 30 degrees. Okay? It's not always 30 degrees. Okay? It depends upon how tall you are, what angle you're pulling it at. But in this particular case, let's say that this person's pulling it at 30 degrees. There is a force of friction of 50 newtons as well, pulling backwards on the wagon. We want to know what the acceleration of the wagon is. Tell me, which way is friction going to act on the wagon, to the right or to the left? To the left. Why is it going to act to the left? Yeah, if you're pulling it to the right and up, it's going to move to the right. Right? This wagon is going to move to the right. That means friction's got to oppose the motion. Friction's going to act to the left. So friction's going to act over here somewhere, okay, and we're going to make that value 50 newtons. Now, there is a force of gravity acting here. And there is a normal force acting here. Do they cancel each other out? No, they do not. Okay, but I'm not going to tell you why right now, because it doesn't really matter for us right now that they don't. Okay, let's just pretend for a moment that they do cancel each other out, okay? We'll deal with why they don't and how that could affect something down the road a little bit later on after we're finished this, okay? This wagon is moving to the right. All we care about are the forces that are left and right. If it's not moving up or down, we don't care about any up or down forces. We care about the 50 newtons because it opposes the motion. We don't care about the 100 newtons per se. Rather, we care about the x component of the 100 newtons as opposed to the y component of the 100 newtons. Does that make sense? Let's find the x component. Let's say cosine 30 degrees is equal to the x component over the hypotenuse, which is 100 newtons. The x component ends up being 86.6 newtons. So what we're effectively going to do is replace that 100 newtons with a force to the right that's 86.6 newtons. Do you see what I've just done? I've got an X, I've got a Y. I didn't really care about my Y because it's not moving up or down. I cared about my X because it's moving left or right. So I turn it into a pretty straightforward problem. Well, now you guys know how to deal with this, right? The net force is equal to the sum of the forces. That's FF plus the applied force, or at least the X component of the applied force. The net force is also equal to M times A. That's 20 times A. It's equal to negative 50, because it's to the left, plus positive 86.6 newtons to the right. 36.6 newtons. And A is going to be equal to 36.6 divided by 20, which is 1.84, 1.8 meters per second squared. Do you see why we've ignored the Y component there? Why do we ignore the Y component? Because it's only moving on the X-axis. Listen, a couple people, when you were working on those other questions on your worksheet, a couple people moved forward a little bit and took a look at questions like this. And people that did, at least people that I saw working on it, had the right idea. In the back of their mind somewhere, they said, I see an angle of 30 degrees. I don't like any angles of 30 degrees. I don't like funny angles. They went back to Unit 1 and said, I don't like funny angles. So they converted that funny angle into an X and a Y component. We just didn't need to use the Y component, that's all. Now, let me go back and explain real briefly here why the normal force and gravity force didn't cancel out this time. I saw on a couple people's faces almost a look like, oh yeah, I get it, I get it. Okay, we'll see how many of the rest of you get it in just a moment here. So here's the wagon again. Okay, there's that applied force of 100 newtons up at an angle of 30 degrees here. We'll call this Fx, the x component of that force, which we just calculated, 86.6. We'll call this Fy. We have a force of gravity acting down, and we have a normal force acting up. It's smaller this time than the force of gravity, and therefore does not cancel gravity, does not balance gravity. Why doesn't it? Why is the normal force this time smaller than the force of gravity, when in every other question that we've ever done up until this point on a flat surface, the normal force and gravity have canceled? Why does Fn not cancel gravity here? Where are you guys that saw, that I saw the look of sudden epiphany on your faces here a few minutes ago? There's 2 or 3 of you. I can't remember who you were, but Austin? Yeah. Look, you ever try to pick up a heavy rock in water? It's easier to lift up, isn't it? It's easier to pick up because of the buoyant force. The buoyant force helps you lift the rock, right? It makes the rock effectively lighter. The actual weight of the rock isn't lighter. The apparent weight of the rock is lighter. The perceived weight of the rock is lighter. But it's easier to lift, right? Why is it easier to lift? Because you pull up and buoyant force pulls up as well. Combined, they balance out that gravitational force or they have to beat that gravitational force that's pulling down. It's easier because 2 forces are helping. Here we've got the normal force pulling up, but it doesn't need to pull up as hard as gravity because, as Austin just said, it's got the Y component helping it. Right? Both the normal force and the Y component help to balance out gravity. In other words, Austin said it in perfect wording here just a minute ago. He said the normal force and the Y component of that force combined, they've got to equal the force of gravity acting down. Does that make sense? See, up until now, it's been gravity balances normal force, but we haven't had that y component of the applied force helping out the normal force until this question. So, in the end, does gravity balance out the normal force? No, but does gravity balance out something? Yes, it balances out the normal force and the y component combined. So, what are we left with? We're left with the force of friction and the x component of the applied force. That's why the wagon doesn't move upwards. You pull upwards on the wagon, but it doesn't go upwards because the y component of your applied force and the normal force combine to balance the force of gravity. Okay? Somewhere intuitively in our mind, we know that when we pull the wagon at that angle, it doesn't go up. Okay? It moves horizontally. Well, then there must be forces that balance there. If it's not going to move up and down, then the up and down forces have to balance. But all of them, not just gravity and the normal force. Right, Kate? All right, what I'd like you to do now is take a look, please, at questions 16 and 17 on your worksheet. And those are the last two that I'll have you work on. 15 asks you for a whole bunch of things. Just ignore 15, okay? Just go to 16 and 17, please, on that worksheet. Okay, let's take a look at 17 here. Question number 17 involves a 10-kilogram object being pulled at an angle of 30 degrees with a force of 30 newtons, force of friction of 50 newtons acting backwards. We have that force of friction acting backwards. We know that it's acting backwards because we know it's going to move to the right. Friction's got to oppose that motion. Now, we also have a force of gravity acting down. We also have a normal force acting up, and we have an x component and a y component of the 30 Newton applied force. Now, the x component has got to stay. The y component disappears along with the normal force and the force of gravity. Force of gravity acting down balances out the force acting up, the normal force and the y component. And that leaves me with two forces. The force of friction acting to the left and the x component of the applied force acting to the right. Let's get that x component. Here's my 30 Newton force. Here's my 30-degree angle. Here's the x component. Here's the y component. Cosine 30 degrees is equal to x over 30 newtons. And that worked out to be 25 point something, I think, doesn't it? 25 point, I don't know. 25 point what? 25.98, thank you. So, let's label that over here, 25.98 newtons for the x component there. Now, let's go back to doing what we always do. F net is equal to the sum of the forces. It's going to be FF plus FX. MA, which is 10 kilograms times A, is equal to negative 15 plus positive 25.98 newtons. It's going to give you 10.98 divided by A, divided by 1. How is that, about 1.1? What do we get? 1 point? 1.098, so it would end up being 1.1 meter per second squared. All right, how many people got that? Good, good. I think we're doing pretty good at this. Okay, guys, isn't it? I need you to take a step back from this for a second and look at what we've been doing for the last couple of weeks. Really, for the last couple of weeks. Okay, we've been doing problems from this, okay, to this, to this, to combinations of those, to this. Now we're looking at problems like this. Except for a few subtle differences, well, sometimes subtle, sometimes not so subtle, differences within these questions, they're all the same. What's common about all of these questions? Every single one of them, F net is equal to the sum of the forces. Whatever forces we have acting here, we add to it. MA is equal to the sum of the forces. They're all the same. Now, this one becomes a little bit tricky because we have to get one of those forces using an angle. This one's a little bit tricky because we have to get one of those forces using an angle. But once we have it, it boils down to the same thing as those first three questions. Is that okay? I don't want you to, like, when you're studying, okay, you're gonna have a quiz here tomorrow, okay? When you're reviewing for that quiz, when you're studying for a unit test, I don't want you to go back and how do I say this? I want you to study all of these questions. But I don't want you to go back and memorize the steps for this question, and then go and separately memorize the steps for this question, and then go and do the same thing for this question. Okay, look at the big picture. They're all the same. We just have to be able to turn each of these different looking questions into that question that's all the same. Sometimes we need to deal with those funny angles. Okay, work on that. Work on dealing with those funny angles, but don't memorize this problem and then memorize this problem. They're the same thing, except for how we deal with the angle. Okay? Well, here's a question from your book that's a little bit different. It's not quite the same thing. Person A thinks that if A and B each pull a rope forming an angle of 20 degrees, the net force on the canoe will be greater than example 3.2. Well, what was the net force in example 3.2? Okay, we were pulling with a force of 60 newtons this way, 60 newtons this way, and there was a force of friction of 85 newtons backwards. What was the net force there? It's going to be 35 newtons, right? The net force in question 3.2 was 85 newtons. In this question, the person thinks that the net force is going to be greater than in example 3.2. So we're pulling along the beach using the ropes that are parallel to the surface of the beach. We're pulling with the forces of, what was it, 60, 60? 60 newtons, 60 newtons. And we're pulling along the same beach, so we have to assume that friction still acts backwards of 85 newtons. Is that person's thinking correct? Is that net force going to be bigger than it was in that last question, 3.2, where the net force was 35 newtons? Okay, interesting here. I see right away, I see one person doing this, shaking their head no. I see one person doing this, nodding their head yes. Who says the net force is going to be bigger here? Who says the net force is going to be smaller here? Who says it's going to be the same? Okay, we had a few people vote for smaller. Nobody else took a stand. Everybody else is a fence sitter. Okay, you got a few people that say the force is going to be smaller. Let's figure this out. Okay, we've got funny angles. What do we say when we see funny angles? I don't like you. The funny angles, that is, not you. Okay, I don't like funny angles. So let's change these 20-degree angles into x's and y's. Let's say cosine 20 degrees is equal to x over 60. Somebody get that value for x. Sine 20 degrees is equal to y over 60. Somebody get the value for y, please. Who's got x? 56 point what, Abby? Okay, 56.38 newtons. What's the y component there? 60 sine 20. I get 20.52. Right? Now, that's going to be the same for both of these because it's the same force and it's the same angle, right? What do you think we're going to do with it at this point? Yeah, we're going to add them, but we've got forces in 2 dimensions now. So let's add them, but let's add them with x and y components. The net force for the x component is FF plus, we'll call this one force number 1 and this one force number 2, plus F1 plus F2 for the x component. We don't need to say m times a for the net force because we're just looking for the net force here, not the acceleration. The force of friction here is negative 85. F1 is positive what? 60? How about positive 56? For both of them. The x component of both of them is 56.38 newtons. What's negative 85 plus 56 plus 56? It's 27.3.76. That's the x component. Now let's do the y component. What's FF? 0 for the y component, right? Because it's all x. What's F1? Well, for the y component, it's, what do we find it to be there? 20.52. What's F2? No. What's F2? Yes. Why negative 20, Oliver? Yeah, because it's pulling downwards, right? Now we add those up, what do we end up getting? 0, right? So in the end, we only have an x component here, but it wasn't as obvious as it was in some of the other questions, right? Okay, we did it in 2 dimensions because we weren't sure that those two forces balanced each other out. Okay? Now, if they didn't balance out, and if you had an x component and a y component, what would you do with them? Let's say it was 10 instead of 0. We'd say 27.76 plus 10. We'd still add them together, but we'd add them together vectorially. Okay. This time we have 27 and 0, so there's not much of a triangle to draw. The net force is just simply what? What was it in the last question? 35? Was the person right? The force is lower, right? Those of you who took a stand when I asked you this question, beginning said the force is going to be lower than it was in the last question. Okay, sure enough, it is. Not a lot lower. But it's a little bit low. Right? It's kind of the same thing as we've been doing, but a bit different now. It's starting to look a little bit different than those questions we've been doing for the last couple of weeks here. Okay. The only thing that I want you to work on now for the rest of class and for homework tonight, questions on page 134. Okay, there's a notation here that I want to point out, okay, that you might not be familiar with. Okay, they give you an angle of 30 degrees and an angle of 300 degrees. What does that mean? 30 degrees is this way. 300 degrees is this way. Okay? Where that comes from is, say this is 0, go around this way. This would be 90. This would be 180. This would be 270. So 30 degrees is right here. 300 degrees is 30 degrees past 270. So just draw that out. The green lines. Don't worry about the red there. You just draw the green lines, 30 degrees and 300, or 30 degrees right here, so that you recognize what that 300 means. Okay, and then you should be able to solve that question, I think. Okay, that's your homework for tonight. Page 134, plus a little quiz tomorrow.